Hello everyone. In this video I'm just going to kind of go on an extension of the last one and do just a couple more examples of solving separable first order differential equations. And it's just in these two examples I'm going to do, you have to either use some sort of technique of integration or fancy substitution to help you out. Alright, so these maybe are a little more involved than the first three examples I did in the last video. Alright, so in both examples we're asked to just find an explicit solution, right, either of the differential equation, which this one is, or the initial value problem, IVP, right, which is the differential equation with some initial conditions that have to be met by the solutions. So one of these is just a plain old differential equation, and the other one is an IVP, an initial value problem. Alright, so hopefully you can tell that this is separable, right? I can separate the variables. Now this function over here, 1 over 1 plus the sine of x, right, only depends on x. There's no other y's, so I can easily separate. So we have dy on the left equals, and then just, I'll do dx over 1 plus the sine of x. Alright, so very clearly separable variables. And again, this whole manipulation, multiplying by dx and whatnot, those manipulations can only be made with first order differentials. Just be aware of that. Right? You're not going to be doing this for second order equations or higher. Alright, and then we integrate. Now the left side's easy. The integral of dy is just going to be y. And then plus some constant, but again, I mentioned this in a previous video. There's going to be plus a constant over here, plus a constant over here. You could subtract this constant to make this other constant a new constant. So why not, so I'm just going to pick one side to put the constant on, and usually I do the right side. Alright, now let's look at this integral on the left. Or sorry, on the right side. So the integral of, dx over 1 plus the sine of x. Alright, so this one, now you could make a substitution here if you wanted, say u equals 1 plus sine of x, but I think that might turn out to be pretty bad. I've got a better idea for this one. Very often, again, not always, but very often, when I see a sum of two terms in the denominator involving a trig function, especially a trig function maybe to the first power, I think conjugates. So let's see how this goes. What I'm going to do is I'm going to multiply the numerator and denominator of this fraction, this is 1 times dx in the numerator, by the conjugate of the denominator, which would be 1 minus the sine of x. And then same for the numerator here. Alright. So now what I have is the integral of 1 minus the sine of x in the numerator, and then I'll just put the dx over here. Just remember that that's part of the numerator, though. That's a factor of the numerator, the differential of x. And then when you multiply conjugates, right, you get a difference of squares. That'd be 1 minus sine squared x. Okay. And the whole purpose of doing that usually with trig functions to bring squares into it is so you could use Pythagorean identities. Remember that the sine of x squared plus the cosine squared x would be equal to 1. So 1 minus sine squared x would be equal to cosine squared x. So I'll rewrite that. So we have 1 minus sine x in the numerator divided by cosine squared x in the denominator, and this hopefully you can see will make this a lot easier to integrate. Because if I go through and divide each term in the numerator by cosine squared, we have the integral of Now 1 divided by cosine is secant, right? So 1 divided by cosine squared, that's secant squared x minus, and then sine divided by cosine squared. Now you could do that with a u substitution, let u be cosine and all that, but sine divided by cosine is tangent, and then you still have 1 over cosine left over, which would be secant. So this is secant tangent. Secant x tangent x, right? That's equivalent to sine of x over cosine squared x. And I'm hoping, again, if you're unfamiliar with these, please brush up. Right? Hoping you recognize these, the antiderivatives of these particular functions. Integral of secant squared would be the tangent of x, and the integral of secant tangent would be secant. The derivative of tangent was secant squared. The derivative of secant was secant times tangent. And then here's where I'm putting the plus some constant, right? Plus some constant of integration. And there we have it. So on the left side I had just simply y equals, and then on the right side this tangent of x minus the secant of x, plus some constant. And this is an explicit solution, right? And that's what we're asked to find, an explicit solution where the dependent variable is solved for, and it's all the y's over here and not over here. Right? So here's an explicit solution to that differential equation, and you can check it, right? Take the derivative of this. The derivative be secant squared minus secant tangent, which you can show is equivalent to 1 over 1 plus sine. Right? So this is indeed a solution. Now another thing I'd like to show you, which I did in my last video on separable equations as well, is this is a first order equation, so I can look at its slope field. So I'm going to pull up a website here, this dy dx equals 1 over 1 plus sine x. And this is the slope field generator that someone created in Desmos. And you put in this line just what the derivative is, what y prime is equal to, or dy dx. So 1 over 1 plus the sine of x. Okay, and make sure you're in radian mode. Okay, and there you go. Here's this slope field, direction field for this differential equation. And then what I'm going to graph here now after that is our solution. Y equals the tangent of x minus the secant of x, and then plus any constant, right? Say plus 2 or something. Why not? And look, now this is blue graph that came up here, right? See the blue graph? Maybe I'll. You see how they're kind of following along. All these lineal elements in the slope field, they seem to be following those directions, fitting into the slope field pretty well, following the flow. Right. Yeah. So it looks like this family of solutions we found is a good solution to that differential equation. Right? Okay, so there's one example where some trig involved, trig identities multiplying by conjugates. Again, there are lots of techniques that you hopefully learned and need just go and brush up on and review from Calc 1 and Calc 2. Maybe it's been a while. Just wanted to show you some. And I got one more here. Just one more example. Again, I'm not doing every possible scenario you'll come across. I'm just doing a few. Right, a few in the last video, a couple in this one. I'm hoping whatever scenario you do come across, you'll have the tools in your pocket to be able to do them. All right, so this one's the initial value problem. All right, so I have a differential equation along with some initial condition on the solution. So the derivative of y with respect to x is equal to e to the square root of x divided by y. And the initial condition on the solution that I'm looking for, the y, is that the value of y at x equals 1 is 4. All right, or the solution passes through the point 1, 4. All right, and I'll show you on the slope field when we're done with this too. When we find our solution, I'll show you that our solution does indeed pass through the point 1, 4. All right, so again over here, this is separable. Right, you can get the y's on their own side, multiply by y on both sides, you get y dy, multiply by the dx, you have e to the square root of x dx. Now the left side's simple. Integral of y dy would be half y squared, right, plus some constant. But again, I'm going to wait to put the constant up on the right side. And on the right side, we have the integral of e to the square root of x with respect to x. Now this here is going to involve some sort of substitution. I hope you see that. Now usually with roots, like this square root of x here, a good substitution is to make, in a lot of cases, not always, but a good substitution to make would be a substitution that would basically just get rid of the root. Now you could have I could let u be the square root of x, or you say that x equals u squared, whichever. Right. Personally, I like this one because it doesn't involve the radical. And if I do this, then dx would be equal to 2u du, right? Taking the differential of both sides, that's 2u du. Sorry about the tininess of that. Alright, then making my substitutions, I'd have 2 pulled outside. Right. So I make the substitutions, because again, dx is going to be 2u du, that's why the 2's out here. And this is u du, and times e to the u, e to the u, du. Right. Now, this integral is one I can do by parts. Right? You see, I have a polynomial times an exponential, and typically, when your integrand has a product of two different kinds of elementary functions, you can do an integration by parts. But since I've already used the letter u, I'm not going to use the letter u again. It might get too confusing. So I'm going to write the parts formula with a letter different than u. So here's the parts formula. Remember, it was the integral of, instead of u dv, how about I do t dv? Right, and that was equal to uv, or tv, minus the integral of v du, but I'll call it v dt this time. All right, just so I don't confuse myself or confuse whoever's reading this with another u. All right, so I'm going to let t be this u here. I'm doing this integral. All right, I'm doing this integral by parts. I'm going to let t represent the u, and then dv be the rest of it, right? The e to the u du. Then I differentiate this, right? Then dt would be equal to du then. Integrate this, you have v would be equal to e to the u. And then put it into the parts formula. Right, so we have taking this down here now, this is 2 times and then the quantity. And then this integral I'm rewriting with the parts formula, right? It'd be tv, so u times e to the u, minus the integral of v dt, e to the u du, and that's an easy one. Or that's just e to the u, right? And then I'll distribute the 2. And we'll also sub back, every u that you're seeing is actually the square root of x. So when all said and done, we have 2 times u e to the u, so 2 times the square root of x times e to the square root of x minus, and then again distributing the 2 times e to the square root of x, and then plus some constant. There as well, I'll throw the constant. Alright, great. And putting both sides on the same line, we have on the left we had half y squared, right, equals, then this 2 square root of x e to the square root of x minus 2 e to the square root of x, and then plus some constant. And then I was asked to find, an explicit solution, but I'll do that after I, find the value of this constant. All right, so now we're going to use the initial condition. So here's a family of implicit solutions to the differential equation. All right, a one parameter family of implicit solutions. Y is not solved for. But now I'm going to use this line to find our constant, right, using the initial condition here. All right, so going back to the beginning, we saw that the value of y when x equals 1 needs to be 4. Right? So the initial condition y of 1 equals 4. Well, let's put that into this equation here, and we'll be able to find our value of c. Okay, so y needs to be 4. So we have half, replace x with 1, y with 4, basically. Right? So half of 4 squared equals 2 times the square root of 1 times e to the square root of 1 minus 2 times e to the square root of 1 plus some constant, and then solve for c. All right, well, half of, this is half of 16, so this is 8. And this is just 2 times e minus 2 times e. So those are gone, and you have 8 equals c. Right, so 8 equals c, that's going to go here. So I've got half y squared is equal to, now, something I'm going to do just to save on a little writing. I know you're probably thinking too late, right? You've already written so much. 2e to the root x is in both of these, so I'm going to factor that out. So 2 times e to the square root of x. I'm going to factor that out, and then when you do that, you'll have the square root of x minus 1. There's another factor here. And then we have plus c, which we found needs to be 8 in order for the initial condition to be satisfied. All right, now this is still an implicit solution. All right, y is not solved for, so now we solve for y to get an explicit solution. So I multiply both sides by 2 to get rid of the half, so we'd have 4 times e to the square root of x times the quantity the square root of x minus 1, and then plus 16. All right, multiply this term by 2, this product by 2, that term by 2. And then something else I'm noticing here too is that both these have a common factor of 4. I'll pull that out. We have 4 times the quantity e to the square root of x times the square root of x minus 1, and then plus 4. And then to get y alone, I would take the square root of both sides. Now be careful. Remember, when you have y squared equals some value, right? Y could be positive or negative. So y could either be plus or minus. Now we have to pick, right? We have to choose which one is going to be used based on the initial condition. All right, so I'll get to that in a second. So y equals plus or minus, now the square root of this, that's why I pulled the 4 out, because you got the square root of 4 is 2, and then times the square root of everything else, right? Times the square root of e to the square root of x times the quantity square root of x minus 1, and then plus 4. All All right, it's crazy looking, but it is an explicit solution, but it's two of them. I got to pick the right one. Now remember, again, the initial condition was this, that y of 1 was equal to positive 4. All right. Well, that means I need to use the plus, because if I use the minus here, this is going to give me a negative. Remember, this is, when you see this symbol, it's the non-negative square root. So if I use the minus sign, my output's always going to be negative, and I'm never going to get a value of a positive 4. So based on the initial condition, I have to choose the plus sign and ignore the minus sign. All right, so my explicit solution to this initial value problem my explicit solution will be y, or y of x, equals, positive 2 times the square root of e to the square root of x times the quantity square root of x minus 1 plus 4. All right, and you can double check. I mean, it'd be kind of a hairy ordeal, but you could take the derivative of this, right, and then plug the derivative back in. Go back to the original, differential equation here. Plug this in for y, take the derivative of this, put it in for dy dx, and see that it makes this true. And also make sure that when x is 1, the output would be 4, which it would be, because if x were 1, this would be 4 in here, 0 plus 4. Square root of 4 is 2, times 2 is 4. It satisfies the initial condition, and it should, if I did everything correctly, and I'm pretty sure I did, it should satisfy the differential equation. All right, and just one more little check for myself here. Again, you can check it by hand. I'm going to pull up again, since this is a first order equation. I'm going to pull up the slope field. So I'm going to enter this e to the square root of x divided by y into that slope field generator, and then I'm going to enter our explicit solution and see how well it follows the slope field. All right, it should follow the same flow, go in the same direction as our slope field. All right, so back here, back up to this g of x, y here. We have e raised to the square root of x. Nope, not that. Then divided by y, and that was our. Now notice how only slopes are showing up to the right of, on the right half of the plane. That's because of this square root of x here, right? You can't take square roots of negatives or you get imaginary outputs. We're not talking about things having imaginary slopes. All right, and now let me get rid of this graph here and then put in the explicit solution that we just found. We had y equals 2 times the square root of e to the square root of x times the quantity square root of x minus 1, and then plus 4, all of that inside the square root. And look at this. All right, there's a solution there, this purple curve that showed up. And you see how it's following along in the same direction as these little lineal elements of the slope field, all these little slopes. It seems to be following in that same flow, that same direction. Looks like it fits the slope curve pretty well, the slope field pretty well. So that convinces me also that this is a pretty good, this is probably a good solution to our initial value problem. And you'll also see that it passes through the 0.14. Right, let me put the 0.14 up here. There it is right there in black, right there. See, our solution passes to the 0.14 as well, satisfies the initial condition. Great. So again, hopefully, again, a little more involved these, but just a couple more examples of separable equations. You solve them the same way, right? It just depends on what technique you need to use to integrate. You separate the variables, get y's on one side, x's on the other, or whatever the variables are. They don't always have to be y and x. Do your indefinite integration, and after that, if there are any initial conditions, you're going to use those to help you find the values of the constants, the constants of integration that come up. And if they ask you for an explicit solution, well, then you're going to have to solve for the dependent variable, right? Solve for y or whatever the dependent variable is in that particular equation. All right, so hopefully watching me go over these couple examples, hopefully this helps you when you're working on similar problems. And thank you very much for watching.